Welcome to the 14th lecture of the course non-traditional abrasive machining processes, including ultrasonic machining, then abrasive jet machining and abrasive water jet machining. So, today we will discuss something about the process parameters and their effects on the response characteristics, and also if time permits we will have a quick look at the take home assignments that we will be sharing between us. So, first of all let us move on to the subject directly. Standoff distance. What does standoff distance mean? Standoff distance means that whenever we are having the end of the tool as a nozzle, and from the nozzle abrasives are coming out at high speed, then the distance between the tool the nozzle tip and the workpiece surface, that is called the standoff distance, and this is generally of a very low dimensional value, say 0.5 millimeters, quite common. So, a very small distance is there. Let me draw a figure so that it is clear to everyone. This is the nozzle and this is typically standoff distance. Okay. This can well be below 1 millimeter. As we go on increasing it up to say 15 millimeters, we will see that consequently this becomes larger in lateral size. If it is circular output, it becomes larger and larger in diameter. Why? Because due to viscous effects, as this becomes slower and slower after expansion, slower and slower, therefore due to continuity it becomes larger and larger in diameter. So, first of all, if you are interested in cutting very precise, thin, narrow lines, okay, if you want to make grooves of very narrow curve fit, if you go on moving away from the nozzle tip, that means if the standoff distance becomes if it becomes higher and higher, first of all this is going to give you a wide cut which might not be your requirement at all. Secondly, initially you will find that the MRR will rise. Why? Because it's a larger and larger area is coming under the effect of the of the jet, and therefore more and more material can well be removed. But after some time you will find that the velocity of the particles becomes so less that they cannot create plastic deformation on the body, they will simply bounce off ineffectively. So, after some time material removal rate will come down. So, if the distance is very small, in that case back pressure will be created, nozzle the what do you call it, the abrasives will not be able to come out at all, and therefore material removal rate will be very low. So, let us have a quick look at the figure. Standoff distance, as it increases, MRR is increasing. Why? Because if you are putting it very close, there will be back pressure and there won't be full expansion of the gases, and it won't be reaching its full velocity. Therefore, if it is very close, you do not have full expansion of the jet, but if you are reasonably away from it, in that case you will have quite a high MRR, and this MRR will go on increasing as the jet becomes wider and wider as we move more and more away from the nozzle tip. That is why with standoff distance it first rises and then it becomes steady when material removal is being caused, and however it is becoming less and less with reduced velocity, and but still material removal has reached a plateau region, because it is encompassing more and more of the surface area and causing damage, but after some time it ceases to cause any material removal, because the velocity has become so reduced, say at around 15 millimeters, it has become so reduced due to viscous drag from the atmosphere, that it does not cause any plastic deformation of the workpiece material. So, this is the way we find is the variation of MRR with standoff distance. Next, the change of mixing ratio causes a change in MRR. Now, what is mixing ratio? Now, if you remember, we have defined mixing ratio according to our definitions, and it is according to our conceptions, and as per our definition, mixing ratio is simply mass flow rate of abrasives divided by mass flow rate of the carrier gas. Hence, mixing ratio, if it is becoming higher and higher, it means that mass flow rate of the abrasive is increasing at the expense, not at the expense, is increasing with respect to the mass flow rate of the gas. Now, if you remember the expression of material removal in case of in case of abrasive jet machining, if you have a quick look at this one, M is proportional to, just one moment, is proportional to MRR. Okay, that looks quite good, looks like a company logo. MRR is proportional to M dot, abrasive mass flow rate, okay, divided by V to the power 3 by 2, rho to the power 1/4, and H to the power, how much? I have forgotten, 3 by 4. So, if you have a relation like this, and if you keep the others constant, in that case, if mass flow rate increases, you will expect that MRR will increase proportionately, and therefore, it will be a linear relationship. Mass flow rate increases of the abrasive and MRR increases linear to it, because there is no power, it is to the power 1. So, if we come back to the figure and have a look once again, then why is the change of MRR initially increasing and after that it droops? This is because if mixing ratio is changing, no doubt the mass flow rate of abrasives is increasing, but it takes its toll on the velocity of the gas jet. Why? Because velocity of the gas jet will go on decreasing if we recall that momentum balance between the gas jet and steady abrasives, abrasives which are in steady state, not moving. In that case, the gas jet velocity gets sufficiently reduced due to the momentum transfer. The abrasives have to be accelerated up to the final velocity of the abrasive and gas jet combined. So, as we are going on increasing M dot, that means abrasive mass flow rate, the velocity of the jet will come down, and that will have its telling effect on MRR. MRR will start drooping. If we come back to the equation once again, let us have a look. Velocity to the power 3 by 2, and this is now going down. If velocity goes down, velocity to the power 3 by 2 will affect MRR in the sense that MRR will go down. So, that is why even if mixing ratio is bringing in more abrasives, their velocity is reducing, and therefore, MRR is ultimately going to drop, increase initially and then drop later on. If we come to the effect of mass flow rate on MRR, it is roughly going to be the same. Why? Because mass flow rate is increasing of the abrasives, and therefore, MRR increases, but as the jet becomes heavier and heavier with more and more abrasive particles, ultimately MRR comes down because the velocity is going to go down, and if the velocity goes down, as we have seen, MRR will go down. Now, we have an interesting graph. The graph is suggesting that if constant mixing ratio is maintained, in that case m dot and MRR will have a directly proportional relationship. That is interesting. Let us see what is constant mixing ratio. It means that if you are increasing m dot, simultaneously you go on increasing the gas flow rate, so that the ratio of the mass flow rates of the two phases always remain constant. So, that means if this particular ratio is constant, velocity of the gas jet will not decrease as previously, but will remain constant, and therefore, m dot will linearly increase MRR as per the equation. So, V remains constant because constant mixing ratio is going to ensure that the flow of the gas jet remains constant, and therefore, m dot directly affects MRR. Now, another interesting graph, that is pressure. How is pressure going to affect MRR? Now, what is pressure? Pressure means that, see, initially we are having a gas cylinder, or we are having a compressor, with the help of which we are inputting the gas at very high pressure, and this pressure head ultimately is going to be converted to velocity head. So, if pressure head is getting converted to velocity head, we can easily write here P by gamma is equal to V square by 2 G. What does this mean? It means increasing the pressure is the same as increasing the square of the velocity. All right. So, that means that if we are increasing pressure, square of the velocity is increasing. That means quite a lot of effect is taking place. Now, let us look at this expression in terms of pressure. Once we know that velocity square is equal to a constant into pressure, we can say therefore, velocity to the power 3 by 2 must be equal to whatever, say k1 into p to the power. First of all, you take away the root, it gets to the power half, you give it 3 by 2, it gets 3 by 2 into half, that means 3 by 4. This is the relationship, equal to constant into what do you call it, p to the power 3 by 4. So, if you have p to the power 3 by 4, after studying about ultrasonic machining, you can very well say that this is to the power 1, this is to the power more than 1, this is to the power less than 1. So, it must be having something of this type, okay? And that is it. If you look at the graph now, this is the change of MRR with respect to pressure. Mind you, here also constant mixing ratio has to be maintained, otherwise what will happen is the amount of abrasives flowing in the carrier gas, its mass flow rate will decrease, okay. As more and more gas is flowing in, its mass flow rate will decrease, and therefore, you are going to have a different MRR. So, constant mixing ratio is maintained here as well, okay. So, this is the effect of pressure on MRR. Pressure to the power 3/4 is MRR is equal to constant into pressure to the power 3/4. So, we have been looking at abrasive jet machining from so many angles. So, let us look at it from the point of view of hybrid processes which have developed with respect to abrasive jet. So, we will be talking about abrasive jet electric discharge machining. So, first of all, as we have discussed previously, before discussing about anything new, first of all we have to check whether it is a purely academic exercise or whether it has any any meaningful implication on the industry. You might ask me, why? Electric discharge machining is quite good by itself. Why do we intend to add suddenly abrasives? So, when electric discharge is dealing with charges, etc., why bring in physical bodies like abrasives? What are they going to do in the first place? So, here we have a rotating annular cylindrical tool, hollow cylindrical tool, where we are giving electrical connection to the tool and the workpiece pair, and additionally we are also providing a very high velocity gas, that means gas at high pressure is being given with abrasive grits. Now, what is it going to do? First of all, as the medium is a gaseous medium, therefore, sparks will be flying from the between the tool and the workpiece across gaseous medium, and this is called dry EDM. Dry EDM has a number of advantages, like it might give us higher MRR, etc., but mind you, dry EDM, the distance between the workpiece and the tool have to be controlled very precisely, because in many cases the distance is much less than that in EDM with liquid medium. It might be as low as 5 microns. So, coming back to this, so first of all, if we draw a figure here and have a look what is going on in this particular process. So, this is the tool, these are the sparks which are flying between the tool and the workpiece, and they remove material by EDM. This one is rotating, this is the axis of rotation. Okay. Now, so this particular tool and here high pressure gas with abrasive particles, they are coming in. So, there must be some problem with EDM alone, because of which this is being employed. What is that? EDM generally almost always covers the surface with recast layer, and if this recast layer is there, if you look at it under the microscope, you will find a lot of cracks and a complete layer sometimes on top of the actual surface, which will detrimentally affect its performance as far as surface is concerned. That means, surface integrity will not be of very high quality. So, if these abrasives are coming, it will find that at this edge EDM has taken place, and maybe recast layer is formed on the surface which we call the finished surface, recast layer. Abrasives will hit, impact this recast layer and be able to remove it. This has a twofold advantage. The twofold advantage is, first of all, the abrasives will be removing recast layer, which is detrimental for surface quality, and secondly, material removal rate will rise, and it has a threefold advantage. The surface finish, which was obviously rough, because some places you have recast layer and some places you do not, and therefore, the roughness would have been quite appreciably high, but once abrasives have acted on that and all metal debris which was sticking to the surface, they are driven off by the abrasives and the flushing action of the high pressure gas, we will find much better roughness will be obtained. So, higher MRR, lower amount or elimination of recast layer and better surface finish. We can expect these 3 points from this particular hybrid process. Okay. Now, next is a small discussion about the what do you call it, the take home assignments that I am going to give you. What are take home assignments? They are not part of the actual assignments which carry marks, but they are for your conception, they are for your interest, and they are for your pastime recreation, if you call this recreation at all. Let us see what does this particular numerical example say. The People's Republic of China floats a world tender for making and supplying metallic logos, emblems, symbols, logos, etc., which has the mainland China map. Only portion B, okay, I have shown it in a small figure at the bottom. Only the portion which is shaded with a dark color and with ashen color, and it is given a name B. Only this part is ultimately going to remain, and the other parts are going to go away. So, in that case, what is the People's Republic of China intending to do? It is planning to make 10 million such pieces, 50 millimeter by 40 millimeter, looks like a small badge. So, these are going to be put into military uniforms, and the logos are to be made from hard, brittle, metallic blanks of 5 centimeter, 4 centimeter, 2 centimeter thick, as shown in figure. Achha. So, A goes away and B will be the logo. B is what we want and A is going to be removed. You plan to through machine the area A by ultrasonic machining. So, you want to respond to the world tender by quoting for, you say that okay, I will make it and this will be my cost. What will be your cost? First of all, what is your technical details for making it? You will be using ultrasonic machining to remove part E. So, if you remove part E, that means you have to have a tool exactly with the shape E, with the B part not there, hollow. So, while using, so you want to use USM, and some data is given about USM. If there is a tool of 100 square millimeters, mind you, this particular tool is not 100 square millimeters, it will having some other area of itself. So, while using a tool of 100 square millimeter area, your ultrasonic machining is capable of removing logo metal at the rate of 100 cubic millimeters per minute, given for USM MRR is equal to K1 into F to the power 0.75 into A to the power 0.25, where K is a constant, K1 is a constant, A is the area of the tool in square meters, and F is the static load equal to 10 newtons that I am providing you. However, you have a competitor, a Chinese company plans to cut along the border between A and B. Chinese company says that I am not going to use USM. You say why? They will say we are free to use whatever process that we want to employ. Yes, ultimately we are supposed to give only the end product, whether I use USM or AJM or whatever, it does not really matter. So, Chinese company plans to cut along the border between A and B by abrasive jet machining, which can cut 1 millimeter thick logo metal at at the speed of 80 millimeters per minute. The relation is given as V is equal to K by D, where K is a constant and D is the sheet thickness and V is the cutting speed. And so, some data is given and the relation is given where, and the logo of area B is of 9.5 square centimeters, and China has a border of 36000 kilometers and an area of 9.5 into 10 to the power 6 square kilometers. These are, actual about China as you see on the internet, these data. And take the scale as area on logo by actual area is equal to length of border on logo by length of actual border square. So, if the cost of both the processes is rupees 100 per minute, answer the following. So, I hope the question is quite clear. You want to use USM, Chinese company wants to use AGM, and now you have to find out which one is going to be more costly. The one which is less costly will win the world tender. What are the cutting velocity, total length of cut and cost of making the metallic logo by AGM? Okay. You have to find out what will be the cutting velocity, what will be the total length of cut and the cost of making the metallic logo. Okay. It should be what are the maximum cutting velocity? You might be cutting slowly. So, what is the maximum? Next, what is the cost in rupees of making the metallic logo by USM? How much should be the static load in USM in newtons, so that the costs of making the part in AGM and USM become the same? Assume the cost of USM manufacturing does not vary with static load. So, you can increase static load, but you have to use that static load so that AGM cost and USM cost become the same. This is take home assignment and you may or may not do it. If you do it, you will come up with an answer. You can send it to me and I will disclose the correct answer at that time. There will be a time given. So, I am not disclosing the answer. If you feel that I should disclose the answer because there is no marking, I am ready to do it. There is absolutely no problem. Next, we have another problem. All these take home assignments will be for your interest, and therefore, they will not be conventional run of the mill experiment, run of the mill questions. KVIC, which reads as Khadi Village and Industries Commission, has developed a manually operated coal chip producing machine. Okay. So, for the villages, it says that you can produce chips of coal from a huge piece of coal and that you can sell in the market. For that, they have designed a very simple machine and they want to give it to those people, needy people, so that they can make a living out of it. It asks your consultancy firm for evaluation of its performance index. Find out the correct values to be put in the last 3 columns of the table. The table is in the next page. Let us see how it runs. Equipment description, hanging coal block. So, there is an upper block of coal, hanging coal block is moved up by leg force. See, there is a rope and there are 2 pulleys and this is the person putting his foot down. Literally, he is putting his foot down and putting his foot up, and this is going up, going down, and in between he has put a granite ball which he can shift and place at different locations, and therefore, there are 2, just like ultrasonic machining, there are 2 chips coming out, one from the upper coal and one from the lower coal, and in that case these are the chips getting formed. And what has been said is that assume that the weight of the upper block remains maximum and unchanged. Naturally, if these chips are coming out, its weight will decrease, but assume for the sake of the sum that is remaining same, and even assume maximum lift for all strokes. Calculate material removed per stroke by energy balance as in AGM. So, if you are lifting the coal to a particular level, it gains in energy, and when you bring it down, it will give up this energy, and this energy, just like in AGM, will cause these 2 indentations, and you have to calculate how much are these indentations. From there, you have to find out the volumes of those coal chips. Okay. Assume 2 hemispherical coal chips produced per stroke by brittle fracture as shown, and this is the table. The table reads number of full strokes per minute will be 30, maximum lift of the upper block of the coal in every stroke is 600 millimeters, maximum weight of the upper block of coal is 400 newtons, hardness and density of coal in GPa, gigapascal and kg per millimeter cube is 0.25 and 750. Diameter of the granite ball is 150, 0.150 meters. Maximum energy input per stroke you have to find out. Maximum material removed in kgs of coal chips you have to find out, and performance index you have to define. Okay. This is the second assignment, a take home assignment question. So, with this we come to the end of the 14th lecture. So, we will meet for the 15th lecture after some time. Thank you.